boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Kat Arney. Hello, Kat.
Hello.
And also with me, Chris Smith. Now, coming up, icy oil. How much oil is there lurking under the Arctic? And moreover, should we even think about going there to look for it? Also, eat oily fish once a week, that's what we're told. But is that sound advice? We've got some biochemical evidence to back it up. And also, where did leprosy come from? A 4,000-year-old body buried in India is just about to give us some vital clues. Kat.
Thanks, Chris. Also this week we're talking biomimetics. That's borrowing from biology. We'll be hearing how scientists have copied the chemical that keeps a bumblebee's wings flapping, and they think that they can use it to beat bad backs. Also how bamboo looks set to be the building material of the future, and how bombardier beetles, which are equipped with their very own high-pressure combustion chambers, could hold the key to better engine efficiency.
We know that we can, without using a huge amount of pressure to atomise the fuel, which is what usually happens, we know that we can do this with much lower pressures, albeit we're using a vapour explosion idea from the beetle, so we are using some pressure, but nowhere near the pressures that people use at the moment.
So it's all the bees this week. Bumblebees, bamboo, bad backs, bombardier beetles, biomimetics. And with all those bees, we've also got some peas, because Ben and Dave will be here later to explain the science of popcorn later in the programme. In the meantime, if you've got a question for us, then do get in touch. Our email address is chris@thenakedscientist.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, we start this week with two very important questions. One, how much oil is there under the Arctic? And number two, should we even go there to exploit it? There's a paper in the journal Science this week. It's by Donald Gautier, and he and his colleagues from the USGS have done quite a clever modelling experiment to work out precisely how much oil they think is under the Arctic. The way they've done this is to basically divide the Arctic Circle, which is quite large, 6% of the Earth's surface is north of the Arctic Circle, into what they call assessment units, AUs. There are 69 of them.
And are these like, they've just divided it up into squares, or what sort of thing have they done?
Well, what they need to do is to focus on areas where there could be oil. So the first giveaway for oil is, of course, rock. You can't make oil if you don't have sedimentary rock. So what they were looking for was areas which had very dense layers of sedimentary rock, in other words, more than 3 kilometres depth of rock. And then the next thing they did was to superimpose on that map, which already had hotspots because that's where the sedimentary rock was, various other geological readouts, so things that we know lend themselves to the formation of oil. Sort of geological formations that form traps, in other words, where something could pool underneath a sort of curved surface, a dome, and it would be impervious rock there, for example. Other sort of data provided by geology companies, drilling companies, petroleum exploration companies, and they've mashed all this data up onto this map to produce this map which gives you some kind of profile for each of those assessment units.
But does it definitely tell us there will be oil or gas there?
Well, what they then did was to compare each of those assessment units with different regions of the world where there are known oil deposits, and they compared the profiles in the areas of the Arctic with the profiles from other regions around the Earth geologically, and said, well, how similar are these bits of the Arctic to these other bits around the Earth? Therefore, how likely is there going to be oil here?
And of course, the $64 million question is there any? How much did they find?
Well, you're going to have to
Can
rephrase that. You're going to have to call it the 64 billion barrel of oil question, because in fact there's quite a lot there. What they come up with, the numbers they produce, is that there could be as much as 13% of the world's as yet undiscovered oil lurking under the Arctic. The total aggregate amount ranges from between 22 billion and 256 billion barrels of oil. Now let's put that in perspective. The Earth consumes annually about 30 billion barrels of oil. So that's between 1 year of world consumption and 10 years worth of world oil consumption annually, just buried under the Arctic. But it gets more exciting, because not just oil up there, of course, lots of gas. In fact, their data suggests that there's 3 times the energy equivalent amount of gas buried under the Arctic than oil. The downside, slightly, for some nations, is that it's all in Russia.
Oops.
So we'd better stay on the right side of the Russians, or we could have a cold winter.
I should think so.
So that's in the journal Science this week, and you can read it up. We'll put a link to it on our website.
Interesting stuff. And now from one type of oil to another, we always hear a lot about good fats and bad fats, and it all gets a bit confusing. But now researchers in the US have studied the effects of the ratio of different fats in human diet and their effect on gene activity.
What actually is the ratio? Because fat's fat, isn't it?
Well, no, there's lots of different types of fat, and over the past century we've seen really significant changes in our Western diet, including a shift in the ratio of certain fats, for example, such as omega-6 and omega-3 fatty acids. Now, omega-6 fats, they're usually the sort of fats found in meat, vegetable oils, and omega-3 fats are found in flax and fish oils, and generally it's thought that omega-3 fats are kind of bit better for you than the omega-6 fats. Now, many researchers have suggested that this shift in fat ratios is contributing to a lot of bad effects on human health, things like inflammation, and this is a key player in autoimmune diseases and allergies, and even in things like diabetes, arthritis, and maybe even cancer. But now, researchers led by Floyd Chilton, and he's writing in the Journal of Biological Chemistry this week, they've carried out quite an interesting little study using human volunteers on a controlled diet to try and understand more about how these changes in the fat ratio might actually affect our bodies.
So what did they do? Did they give people different amounts of fat to eat?
Well, it was a very simple study. Now, what they did is they looked at the evidence from history, and this suggests that our prehistoric ancestors lived on around a 2-to-1 ratio of omega-6 to omega-3 fats. But in recent years, our Western diet has a ratio of around 10-to-1, so a lot more meat fat in our diet compared to fish fat. Now, what they did was they took 27 healthy volunteers and they fed them on a controlled diet containing this lower 2-to-1 ratio of omega-6 to omega-3 fats. Then they measured the activities of certain genes and certain markers of inflammation and immune activity. And maybe unsurprisingly, they found a significant drop in the levels of these important molecules, in particular one called PI3 kinase, which does play a crucial role in early inflammation.
Two things though, Kat. I mean, one is that this is a very small study, so you have to be cautious how you interpret that. And two, when you enrol people in a study like this, is there not a danger that you could change other things without realising it? In the way they eat, the way they behave, that kind of thing, and that could have a knock-on effect and make it look like you've done better.
Absolutely. I mean, it's a very small study. It's still really early days for this kind of research, but it's a very tantalising glimpse at what might be possible through manipulating the ratio of fats in the diet and maybe explaining why we see so many of these sort of autoimmune and inflammatory diseases nowadays. So watch this space.
Well, I'll certainly be tucking into my mackerel later. Oily fish.
Good plan.
Definitely. Now, very interestingly, this week, scientists have uncovered what they think is the world's oldest example of a leprosy victim. This is a paper in the journal PLOS One, and the pictures are absolutely stunning. I mean, take a look at this beautiful skull.
They're stunning, or that just looks a bit
to an
horrible.
archaeologist. This is Gwen Robbins and colleagues who are based at the Appalachian State University in North Carolina. They've been working in a place in northwest India. This is Balatal, who's up in the northwest of India, and they have excavated a site which goes back, it can be very carefully dated, to about 2000 BC, so that's 4,000 years ago. And they've found the remains of a 37-year-old man. We know it's a man by looking at the shape of the pelvic bones, because men have a different shaped pelvis to women. And this body, the skeleton, shows very characteristic bone changes, like these shown in the paper. If you look at the skull here, you can see this, what's called reactive flare on the surface coating of the bone above one of the eye sockets. There's also a complete hole in the bone adjacent to the underside of the nose, and there's also damage under one of the eye sockets and also in the backbone. Now,
well, it's full of holes and it looks manky, but how do you know that that's leprosy?
Well, for a long time people have said that there are a number of diseases that will cause similar bony changes like this. Syphilis is one of them. There are others. But the reason that this seems a good sitter for leprosy is because, A, we can place it in space and time. There are historical records that go back to within 500 years of this. No archaeological evidence, but historical records. In fact, there's some Sanskrit hymns which talk about this kind of disease,
nice.
which puts it in the right place at the right sort of time. And two, it coincides with what we know people were doing at this time. We think leprosy possibly originated originally in Africa, and that as people migrated out of East Africa, perhaps they took it with them. It might be that it didn't originate there at all. It could have originated where this person was found, in India. And why this is so important is it coincides with early civilizations going from being nomadic hunter-gatherers to forming villages and towns supported by agriculture and keeping animals, and therefore living together and therefore facilitating spread, because leprosy is a very low infectivity, but it is nonetheless an infectious illness. You do spread it, we think, possibly by respiratory droplets from one person to the next. So it needs people to be in close contact because only a small minority of the population are susceptible. Therefore, you need a big population living together to get enough people spreading it around to keep it circulating. Otherwise, it just would die out. So that's why they think that this is important archaeologically, for the simple reason that it's in the right place at the right time, and suggests that this disease probably came around about 4,000 years ago.
Fascinating, when archaeology and pathology collide.
Well, the archaeologists love it because they've beaten the historians for once.
Good on them. So from very old things to very new things. And we all need new cells created in our bodies, for example, to replace dead or damaged cells that we might have. And they don't just appear from nowhere. They're created by the division of one cell into two new cells. And this process is called mitosis. Now, scientists at the University of Michigan have used a clever laser technique to get an even closer insight into how mitosis works and how it might go wrong in diseases like cancer when cells just divide out of control.
So when you say divide out of control, how does that compare with what normally goes on?
Well, normally in mitosis, cells first copy all the DNA that they have, then they line up these two sets of chromosomes in the middle of the cell, and thanks to a microscopic scaffold-like structure called the spindle grows in from each side of the cell, it attaches to the chromosomes, and eventually pulls them apart in opposite directions. So you get a copy of each new DNA in each new daughter cell. Now, if this goes wrong, then the new daughter cells may end up with the wrong number of chromosomes, and that spells bad news. And for many years, researchers have tried to understand how the cell manages to divide its chromosomes equally between daughters. And now, new research in this week's edition of Current Biology by Alan Hunt and his team may help to explain why.
So what have they done?
Well, the Michigan team have used high-speed lasers to slice off tiny pieces of chromosomes from within living dividing newt cells. They're using newt as a model organism here, and they watched what happened. Now, the pulses of this laser light lasted for only a femtosecond, that's a billionth of a millionth of a second, but they were enough to cut the chromosomes to slice them with that laser power. Now, previously, researchers had thought that something called polar ejection forces, which sounds brilliant, it sounds like something off Top Gun, were at work in dividing cells, helping to maintain this tension across the spindle and ensure that an equal number of chromosomes go to each new cell. Now, Hunt suspected that these forces should actually be directly related to the size of the chromosome. So if you cut off measurable chunks of chromosomes, then you should have a measurable and proportional effect on the pull on the chromosomes, on the spindle. And that's what they discovered. They discovered that these polar ejection forces are also an important physical cue. It's actually the force is the cue that helps cells to control mitosis and the direction of chromosome movement, so that making sure that the chromosomes go to the right side of the new cells.
Well, that's very interesting, isn't it? Because, of course, one major disease which occurs when genetics goes wrong is cancer. Cancer's a genetic disease. So does this help us to gain insights into what's going wrong with cancer?
It's certainly really interesting from a cancer perspective, because it does shed light on how the fundamental process of how cells are multiplying, and also on chemotherapy, which actually works to block mitosis in many cases, many types of drugs. But it also helps us to understand how damage might occur in cancer, how you might end up with the wrong amount or broken chromosomes in cancer cells, and also other diseases, things like Down syndrome, that are actually caused when egg cells divide by the wrong number of chromosomes going into the new eggs, and that leads to these kind of problems. So potentially lots and lots of interest in there.
Thank you, Kat. And again, you can read a bit more about that from our website, where we'll put the write-up and the reference, nakedscientists.com. Now, also in the news this week, researchers have discovered a far more diverse collection of bacteria living on our skin than we thought was possible before. And it turns out that it's not just our good old friend Staph aureus or other species of Staphylococcus that lay claim to our bodily surfaces. And tell us a bit more. Here is Julie Seagray. Hello, Julie.
Hello.
Welcome to The Naked Scientist. You've published this wonderful paper in Science this week about this. How did you go about mapping what bugs were living on who and where?
Well, it's really quite straightforward because the skin is so accessible. So we asked healthy volunteers to come into the NIH Clinical Center, and we took something that looks very much like a Q-tip, and we just swabbed the bacteria off the different parts of their body, everything from their forehead to behind their ear to behind their knees to underneath their foot and between their fingers. And then instead of culturing these in the lab, which has been our traditional method for knowing what bacteria reside on the skin, we sequenced the DNA immediately. So there was no culturing. We just looked at the signature of each bacteria by its DNA sequence, and those sequences are unique enough that we could say this is a staphylococcus, this is a streptococcus, this is a corynebacterium, and we found an enormous diversity of bacteria that we really hadn't appreciated before.
Because when you put things in culture, of course, there's a selection applied. In other words, some things won't grow in culture, so scientists would have missed them before. But by using genetic techniques, you're able to see what we couldn't see before. How are you then going to take that further? What can you tell us about the spectrum of bugs that are on the body surface and how they might be linked to various diseases, for instance?
Well, this is a baseline, and the studies that were done previously that were based on culture really gave us an incomplete view. Now, some of these bacteria actually, now that we know that we're looking for a Pseudomonas or we're looking for a Corynebacterium, we can now culture them. And it's the interesting thing about culturing bacteria is it's very hard to know what you don't know, but it's easy to find what you are looking for. So now we tailor the media. For example, a lot of the bacteria live on the oily surfaces of our skin. And when we really just add lipids or oil to the culture broth, now we can grow these bacteria. We just didn't know they were there before. This gives us a baseline so that we can now begin to examine in eczema, psoriasis, acne. We can begin to ask what is different besides just even what we can culture in the lab. How has the microflora changed? And then how do we have tailored therapies to bring it back into balance?
Because some people have suggested that some of those skin conditions that you cite are aggravated by the presence of bacteria, and that in fact they drive or stimulate the condition and make it worse. It's not so much that it's just because there's damaged skin there, it's the combination of some damaged skin which gets these bacteria in there in the first place, and then they make the problem worse.
That's absolutely right. Something like eczema has a very strict connection with a Staphylococcus aureus infection. Then there are other diseases like the MRSA, the methicillin-resistant Staph aureus. We know that's a bacterial infection, but we also know that a lot of people have a small, tiny, tiny amount of MRSA that you could find in their nose. They never get an infection. So we're suggesting that it might be the healthy bacteria, the commensals, that keep those pathogenic bacteria in check.
I was just going to say, because we have come round to the idea in recent years that having a healthy intestinal bug spectrum helps to protect us from various things. If you go to a foreign country and you don't get traveller's diarrhea because you have a healthy microbial flora, could the same be true of the skin? And in fact, people in whom there is some kind of problem with their normal skin bacteria, it makes them more prone to getting infections that a person who doesn't have that problem with their skin flora wouldn't get.
That's such an interesting idea to pursue, because it's interesting from the perspective of science. I think that's absolutely right on, and that's where we're going to go with these experiments, is to understand maybe why someone has a predilection for developing a skin disorder based on a change in their microflora. It's also interesting from a societal perspective. Why is it that we want to eat probiotics and balance our gut microflora, but we want to sterilize the outside of our bodies? We have to realize that there are healthy bacteria that live on our skin and that we need to promote their growth. I'm not talking about letting everything grow in your skin. There are a lot of transient bacteria that are bad, and I'm a deep believer in personal hygiene, washing your hands and using soap and all sorts of products. And I think there's a great use for all sorts of skincare products, but I think we also need to recognize that the goal is balance.
I was just going to say, Julie, have you been in the shower this month? No, I'm just joking. But so basically the way forward now is to begin to say, well, how do we tie different bacterial populations to different diseases or lack of diseases? Can we understand more about what's healthy? And in the long run, perhaps we're going to see skin creams that are not designed to abolish bacteria, but to encourage the ones we do want, not the ones we don't.
Absolutely. And I think there also are intrinsic changes to our skin. The skin of a baby is not the skin of a teenager, it's not the skin of an older person. So we have to understand that these things change with time, and that as we change the environment in which we live, we may be altering the microflora. I think these are going to have profound effects on both common and rare skin disorders.
Julie, we'll have to leave it there. Thank you very much for joining us.
Thank you so much.
That was Julie Segree, who is from the National Human Genome Research Institute in the US. She's got a paper in Science this week in which she sets out basically what's living on you.
Distilling the best science. The Naked Scientists.
You are listening to The Naked Scientists with me, Kat Arney, and with Chris Smith. Today's show is all about bioengineering, taking mechanisms from nature and plugging them into technology. So how can the cinema favourite popcorn provide us with new engineering ideas? I think it's time for a bit of kitchen science with Ben and Dave to find the answer.
For Kitchen Science today, Dave has actually come to visit me in my own kitchen, and he's brought along a huge bag of popcorn. Now, I'm assuming that I'm going to have to dig out a DVD, we're going to fire up some popcorn and watch a film, but that doesn't really feel like a science experiment. Dave, what are we doing?
We may be onto the film later, but first we're going to do a little experiment with popcorn.
Well, I always enjoy eating popcorn. It's quite good fun to cook as well because of all the popping, and inevitably you get kernels and cooked popcorn all over your kitchen. But what are we actually doing? What's our experiment?
We're going to be having a look at how the popcorn pops. And what we're going to do is we're going to try popping some normal popcorn, just straight popping corn into a hot saucepan with a bit of oil in the bottom. Obviously be very careful because it's very, very hot. And then we're going to get some popcorn and just crack some of the kernels and see whether it works as well.
Popcorn kernels are really hard, though. When you say crack them, how are we going to do that?
Well, I found one of the easiest ways of doing it is just with a pair of pliers. I've got a nice big pair of pliers, a little gap in the middle for hanging onto tubes. If I just squeeze gently.
Okay, so we're not crushing them, you're not sort of powdering it, it's just enough to break it.
Yeah, just there's a couple of cracks on the outside of it.
Okay, so we need to compare some normal popcorn to some cracked popcorn. And I'm guessing we're going to see which one tastes best.
Which one tastes best? Which one looks best? Do you know which is the best?
Okay, well, we better get cracking some popcorn so we have a good handful that we can test. And we'll be back later in the show.
A cracking experiment there from Ben and Dave. So what you do is take a handful of popcorn kernels, give them a good seeing to with the tool of your choice, and then apply some heat.
This is The Naked Scientists with Chris Smith and with Kat Arney. This week we're talking about biomimetics, borrowing from biology. And it's not just popcorn that goes pop, incidentally, because bombardier beetles are known that way, because they quite literally bombard their predators with explosions from their rear ends. They can actually expel boiling liquids over distances of a few feet. And now researchers have worked out how they do it, and by copying their strategy, they're hoping to build better aerosols and also more efficient engines. And one of the scientists who's doing that is Andy McIntosh.
These insects, bombardier beetles, are found mainly in the hot parts of the world, although I believe they have been discovered even on the south coast of England. They can be as large as 2 centimetres, but usually they're a bit smaller than that. And they have in their backsides a most amazing combustion chamber, Chris, which is about 1 millimetre long or smaller. And they mix 2 chemicals, hydroquinone and hydrogen peroxide, even before they come into the chamber. Nobody quite knows why they don't react in the very small tube that comes in. And in the chamber there is a mixture now of catalysts, peroxidase and catalase, which cause the reaction to go much faster than it normally would, which then heats up the water which is also there. It tries to expand, but it can't initially expand, and it can't vaporise, therefore, and boil properly until an exhaust valve, which is just a bit of cuticle which won't really give way until there is a pressure rise sufficient to make it give way. And when that goes, then it basically suffers a vapour explosion. And this all happens in 1/400th or even 1/500th of a second.
So this is like you unscrewing the cap on a radiator of a car engine that's hot and the water's suddenly boiling when the pressure goes off. So
Exactly.
This is happening in the back end of this insect.
All the time when it's doing this, yeah. And it will do it for about a few seconds. So you're getting a huge number of blasts. You know, if it goes on for 10 seconds, then obviously if it's doing it 400 times a second, you can work out how many blasts it's doing.
And why would it do this?
Well, basically, this beetle is being preyed on, at least creatures like birds, spiders, ants are trying to get at this creature, and they usually don't win. Very rarely a spider might be able to wrap it round in its web and eventually eat it, but that's rare. They're usually stunned by this horrible mixture, which is hot. And although they won't be killed by it, they'll be so stunned that they won't be able to do anything for a few moments, and then the beetle runs away.
It's an intriguing adaptation. It's amazing to think the beetle doesn't actually burn itself in the process. There must be some kind of adaptation that protects it. But when you sort of zoom in on the apparatus this beetle uses to do this, what does that tell you about how it works?
Well, as I mentioned earlier, there is an exhaust valve which doesn't give way until there's a particular pressure. And also you should note that there is an inlet valve, which is, as the explosion takes place, there is an expansion which causes the whole chamber to begin to pinch the inlet valve, such that as it explodes, that stops more stuff coming in. What we didn't realise was that there was an exhaust valve which was really made out of a bit of a cuticle which would only stretch under a particular pressure. We reckon it's about 1.2 or 1.3 bar, but we're not really quite sure. Nobody's been able to get an instrument small enough to measure it.
The one thing that strikes me when you hear a story like this is you're saying to yourself, there are so many applications for what amounts to a spray gun. Could you copy this?
Yes, just be aware, though, that people are already using this pulse combustion idea for engines. There is such a thing as a pulse combustor engine. And indeed, it was used, by the way, in the V1. The Germans didn't realise, of course, that was the same as what was happening with the Beetle. So without realising it, people have been using this type of idea already. But what is unique about this, though, is that it gives a facility for, if we can copy it, for actually getting a spray of liquid and controlling the droplet sizes if we know how to get the valve system working properly. So rather than relying on a passive system, which is what the Beetle does, we have introduced an active system whereby we control when the inlet of water comes in and the outlet of steam and water takes place. And we're able to actually use the idea of the Beetle, not on the chemistry, but on the physics of this valve system, to be able to actually get some very unique spray gun, as you call it, applications.
Engines have to atomise fuel to get the fuel into the cylinder quickly and in a very widely distributed and with a very uniform particle size, because that means the burn will be better. So I would think engine straight away.
Absolutely, and that's one of our major interested areas that we're developing. We know that we can, without using a huge amount of pressure to atomise the fuel, which is what usually happens, we know that we can do this with much lower pressures, albeit we're using a vapour explosion idea from the Beetle, so we are using some pressure, but nowhere near the pressures that people use at the moment. Also, there's aerosols and other applications which this could be used for, maybe pharmaceuticals as well.
I was going to say therapeutically, because there are instances where you want to get very uniform, very fine droplet, nebulised mixtures, for example, that will then be carried on the airstream deep into someone's lungs. Could you do something like that with this?
Yes, we think we can, although I think that's a little bit of a long way off at the moment, but we're pretty sure that just by using water, not fuel obviously, as in the fuel injector idea, but just using water, we think we can use that as a spray which can produce steam and water, which actually cools down pretty quickly and can take a drug which is in solution into a targeted area in the patient. We're not quite sure yet whether this will work out, but we're certainly looking into that.
And that was Leeds University's Andy McIntosh, who's working with the organisation Swedish Biomimetics 3000 to copy the Bombardier Beetle's spray technique.
Thank you, Kat. Now, in just a moment, we're going to be finding out about wind turbines that are made of bamboo. Who would have thought it? An age-old material that's actually cutting edge. And also, why sunflowers manage to point at the sun all the time. What happens at night time? How do they get back to where they started? Well, we've got the answer. But before then, we're exploring how biology can influence technology, and a very springy example is the stuff that keeps the wings of a bumblebee flapping. And joining us from the CSIRO's headquarters, I suppose you could say, but in Queensland, Australia, he's here in Cambridge for a meeting. That's Dr. Chris Elvin. Hello, Chris.
Hi, Chris.
So tell us a bit about this chemical that keeps a bumblebee's wings springy.
So this is resolin. This is a protein. That's a polymer of amino acids. and it's found in probably all insects, where it enhances the efficiency of insect flight. And it was discovered by a Danish researcher here who became Professor of Zoology here in Cambridge back in the 60s. And he did some very elegant experiments to show that this was an almost perfectly elastic material. In other words, it loses almost no energy as heat when it's stretched.
So you stretch it and then let it go, and it returns all of the energy you've put in.
Exactly. Nearly all of the energy that's put into it is returned, about 97%.
And chemically, how's that achieved?
It's achieved by having an almost completely unstructured, random structure to the protein, if you get what I mean. And it's cross-linked. There are covalent cross-links between chains of the proteins that allow it to act as a random network polymer, which is exactly what you need if you were designing a perfectly elastic polymer.
And how does nature use it?
Well, it's as I said, it's present probably in almost all insects that have been looked at, and we've certainly looked at it at the gene level in fleas, in dragonflies, in buffalo flies, and in Drosophila. We've pulled those genes out. So
I think mechanically what I'm getting at is you've got wings. How is it attached to the wings, or is it actually intrinsic to the wing material? It's
both. It's found in the joins of the wing veins in dragonflies, for example, but it's also found as a major component in a tendon which is attached to the muscles, which are attached to the wings, and it's that large tendon that Weiss Fogg worked on back in the 60s and poked a tiny little silver wire down through the hole and hung weights off this thing and showed that when he released the weights it sprang back to exactly the position it was at the start and so on. So it's there to on the downstroke when the insect uses its muscles to pull down, this tendon is stretched, and then the energy that it's stored is released when the wings come back up.
And why is it called resilient? Is that presumably because it's very resilient?
It's from the Latin resilia, to bounce back, and he named it resilin.
Ingenious. So obviously something with those kind of properties would be extremely useful if we could work out how to make this stuff.
Absolutely. So we've taken a part of the resilin gene from Drosophila, and we published this in Nature back in 2005, and we were able to express just a part of the gene in E. coli. So we turned the E. coli bacteria into little factories. They made the protein. It was a protein solution, and we cross-linked it using a photochemical method. So we add a catalyst, a photochemical catalyst, and an oxidant, and we flash it with white light, and it turns from a liquid into a rubber, which displays many of the properties of the native material.
So what you're basically saying is you can steal the gene from the fly, get bacteria to make a sort of precursor form, which you're then able to activate.
That's it.
How much can you make?
We could theoretically make kilos of it if we needed to. I mean, we've made 100 grams or more in a large fermenter at CSIRO in Australia, and we can then purify that protein using some neat protein chemistry techniques and get it almost pure, and then cross-link it with light.
So say you wanted to make a structure with this.
Yep.
We sold this on this week's show as bad backs because I think the stat you told me when I spoke to you a few years ago was a person bends their back about 100 million times in a lifetime.
That's it.
A bumblebee flaps its wings 500 million times in a lifetime. Therefore, we think this protein could be used to repair bad backs. But tell us how.
Sure, that's the interesting bit, and what you want for a spinal prosthetic disc, because that's after all we're talking about, is are a number of things. One, you need to have a material with very high fatigue lifetime, and you mentioned the 100 million cycles. It's a number of times we move our back in our lifetime, and this material, from a materials point of view, has that specification. It can at least last that long before the bonds start breaking down. What you also need, though, is for the material not to degrade. This is a protein. It has peptide bonds in it, and proteases will break it up. So we need to make it non-proteolytically sensitive.
Can you do that?
Yep, we can. And we have a project, an ARC-granted grant project with Monash University, and the plan there is to use non-natural amino acids, so beta or D amino acids, which aren't recognised.
Oh, very clever. So by using things that you wouldn't normally find in the body or in nature even, and so they have the same chemical properties.
That's it.
But they don't look right.
That's it.
Therefore, they can't be broken down by enzymes.
Exactly.
Ingenious. And so you could then cast a sort of disc.
You could.
And put that into someone's bag.
You could.
And when will we see this? Will this be in time for the fact that, I've been doing a lot of digging, Chris. My back feels a bit sore. Is this going to be within my lifetime, or is this way out there into the future?
I would think we're probably talking 10 years, probably. There are some other things that need to be done to it too to make it. It's very soft material. Insects are very small; they don't need to have very stiff springs, so it needs to be stiffer, and we can do that as well. And we've got some ideas to do that.
It puts a whole new meaning on that movie, The Fly, doesn't it?
It does.
Thank you for coming to join us. That was Chris Elvin, who's researcher from the CSIRO in Australia. I wish you luck and have a wonderful trip back to Australia.
Fantastic. Thanks for having me.
Wonderful country, and it's good to have you here in England. That was Chris Elvin, as I say, from the CSIRO, explaining how he has worked out how you can make the gene product of resilin, this protein that keeps a bumblebee's wings flapping, in the laboratory. I might be able to make my back better when I get old.
And mine too, I hope. Oof. Anyway, now from beetles, we've heard how beetles inspire aerosols, and now we're going to join Meera Senthalingam, who's been finding out how biomaterials can even revolutionise our energy industries, in particular wind energy. She went to meet Jim Platts from the University of Cambridge, who's using bamboo as the core material for the production of wind turbine blades.
Because wind turbines are a rotating machine, but they're in the turbulent boundary layer of the atmosphere, they suffer very much from fluctuating loads. The materials that are best for coping with that are fibre-reinforced materials. Metals aren't so good. So we can all easily think of glass fibre, of carbon fibre, of fibre-reinforced composite materials, but actually wood is a naturally occurring fibre-reinforced material.
What makes bamboo more appropriate than other types of wood?
Many common species of wood have got fibres running in many different directions, so a block of wood is strong in all directions. Some materials, bamboo is a particular example, but you can also think of fir trees maybe. The fibres in the wood are running along up the trunk of the tree or up the stem of the bamboo if it's bamboo.
Running only in one direction?
Yes. If they're all running in the same direction, it gives you much better properties in that direction.
And why is it more beneficial for a blade to have unidirectional fibres?
Well, a blade is itself rather like a tree. It's fastened at the root end of the blade, and then it's a big, long, cantilevered beam sticking out, picking up what are heavy loads from the aerodynamic loads from the wind at the tip. So it's bending the blade, just like a tree is bent when the wind blows. So you want the fibres running along the blade to give it the tension strength and the compression strength where the beam is bending.
What actually happens to incorporate wood from bamboo into a wind turbine? So you have a piece of bamboo in front of you. What happens to it to then make it a blade?
When we're talking about bamboo, we're talking about moso bamboo. Moso bamboo typically grows 12-15 metres high. The stem is, say, 120 millimetres diameter, and the wall is, say, 15 millimetres thick. So this is big stuff. What we want is what I call the skin of the bamboo, the last 1 or 2 millimetres towards the outside, because that's where the fibres are most densely packed, and so that's where we get our highest strength. And the rest of the bamboo can still be used for furniture and anything else you like, but this is the really high-tech bit. We then take those strips and stick them together one on top of the other to make a plank, and then to make the aerodynamic shape of the blade, all these planks, we lay them side by side, end to end, all the way up the blade to give us the structural strength. And then when we've laid them there, we cover it with a polythene bag and suck the air out and let resin flow in to stick them all together, which makes one completed structure with a fiberglass skin on the outside to give it a hard surface, but then all these bamboo strips stuck together inside, giving it the technical strength to do the job.
Now, you actually have a few samples of some planks of bamboo and things like that here with you now. There seems to be lots of these planks just put side by side, and you've put a layer of resin, and it's very solid, actually. You can't even feel any gaps between these planks being side by side.
Yes, that's exactly right. The resin is doing two jobs. It's sticking all the planks together to give us the strength, but also one of the things which is very important about wood is it has its best properties when it's dry. So we have dried the wood, the bamboo, before we use it. And when the resin soaks around it, this is epoxy resin, and epoxy resin is a complete vapour barrier. All the electronic chips and so on in your computer or your pocket calculator or your mobile phone are all soaked in epoxy to keep the moisture off them. And we do the same with the wood.
And there's also the extra advantage of the fact that bamboo has a negative carbon footprint.
Yes, if we compare bamboo to glass fibre, to carbon fibre, we use a lot of energy melting the sand to make the glass, to make the fibres, for instance, for glass fibres. That energy produces a lot of CO2. Because bamboo is something that grows, it's a natural product, it is actually a carbon sequestration process itself. It's taking CO2 out of the atmosphere and it's making a high-quality structural material out of it. And over the 20 years operating life of the wind turbine, it will give you as electricity 400 times the fundamental energy content in the bamboo that went into the blades, which is a sort of huge payback ratio. And in the process of using the bamboo, the CO2 has been locked up in the bamboo, in the blade. So it's got a negative carbon footprint, but a huge energy payback on that investment of it.
Now, just to get a few kind of facts and figures about this then, a typical turbine made of bamboo, what would it look like? How big would it be? And how much energy would it produce?
Typical wind turbines these days would be a tower, 80, 90 metres high. The rotor on the top of that, 80 metres diameter. Typically, wind turbine blades, 40 metres long. 3 of those 40-metre blades are on the hub. That is 1.5 megawatt electricity. And you'd normally have those in a wind farm of tens, maybe even hundreds of wind turbines, making a significant-sized power station.
Now, whereabouts in the world is bamboo going to be used? Because it's obviously not native to the UK or Europe.
There are several major countries that have big bamboo resources. The industry is beginning to develop the bamboo technology for wind turbine blades in China. I think people are going to become hungry for this technology.
So, bamboo is a strong contender for turbine blade manufacture, and it also apparently has a negative carbon footprint. That's pretty important in the current climate. Boom. Anyway, that was Jim Platts from the University of Cambridge talking to Mira Senthillingham.
Keeping you abreast of the world's best science. The Naked Scientists.
You are listening to The Naked Scientists with Chris Smith and Kat Arney. And now, because it's been such lovely sunny weather, here is the woman who brings sunshine to all our lives. It's Diana O'Carroll with Question of the Week.
Well, I'm definitely wearing the factor 50 million today because I'm a bit ginger. I have to. But anyway, this week has been pretty good for sunbathing weather for plants.
Hello there, Naked Scientists. This is Sarah Miskimming from West Sussex. I've grown sunflowers in my garden for several years now, and they always follow the sun round from east to west each day. But what I would like to know is, do they slowly unwind during the night so that at sunrise they are pointing east again, ready and waiting for the sun up? Or do they remain facing where the sun set in the west until the sun starts to rise and then suddenly whiz round to face it? Also, if it's a particularly clear night with a bright full moon, do they turn to follow that too? Many thanks, Naked Scientists.
So what is the mechanism that put the sun in sunflowers?
So my name is David Hankey, and I'm a university senior lecturer at the Department of Plant Sciences here in Cambridge. It's actually very simple. There's a kind of driver, which is actually growth. It's all down to growth. If you look at a sunflower, there's a narrow neck while it's growing. And it's in this narrow neck that most of the cell expansion and therefore the elongation of the stem is taking place. And it takes place at different rates on different sides of the stem. So during the early part of the day, most of the growth is taking place on the west side. So the flower is tilted towards the east. And then as the day goes on, then you get stronger and faster growth on the north side. So the flower becomes tilted. And so on all the way round through to the evening when it ends up pointing west. And during the night, what happens is the growth is corrected. So you have a great deal of growth that takes place now on what is effectively now the west side to turn the whole flower over so that it ends up at the beginning of the day pointing east. And that pattern is probably driven by a kind of internal clock that's set by the transition at the end of the day from light into darkness, that then starts the whole process of, as it were, west side growth in the flower. We know that the sensitivity of plants to light, in terms of the sensors which plants have capable of picking up light, are quite remarkable, and you can show that the light of a full moon on a completely clear night is just about perceptible to a plant. And the problem is that most of the time the moon isn't full.
Sunflowers do unwind at night using the same alternating growth mechanism, and it is possible that they could follow a full moon too. What's interesting is that no one really knows why the flowers themselves follow the sun, but best guess is that they need the extra heat to grow more seeds. As Chemistry for Me noted on the forum, once they've lost their seeds, they just sit facing east all day long. But from natural wonders to natural disasters for next week's question.
Hi, this is Mike calling from the United States in Tucson, Arizona. Love your guys' podcast. It's great. What I was wondering was what would be the short and long-term difference if a significant, like a dinosaur-killing type asteroid or meteor would impact the Earth in either a land mass or in the deep ocean or polar ice cap.
So where would you tell an asteroid to go if it was coming your way? Send your answers and new questions to chris@thenakedscientist.com or write it for all the world to see on our forum. And you can find that at thenakedscientist.com/forum.
Thank you very much. That's Diana O'Carroll. And one thought I did have when you were saying about sunflowers following the sun round and then they lose interest once they've had their flowers and made seeds. As Beverly Glover, who we've interviewed on this programme before, found out 3 years ago, flowers warm up. They act like solar cells because it makes them more attractive to insects. And it might be that the flower gets warmer because it faces the sun. This pulls in the pollinators. Once it's pollinated and got seeds, it no longer needs to do that.
Apparently it's a 10-degree difference if it faces the sun for a long period of time.
Fantastic. You can find out more about Question of the Week from our website. That's nakedscientist.com/QOTW. Or you can hear Diana in her own right on the Question of the Week podcast, which you can get from iTunes.
Lifting the lab coat on the world's best science. The Naked Scientists.
This is The Naked Scientists with Chris Smith and with Kat Arney. We're talking about borrowing from biology this week, biomimetics. So if you have any questions on that, the email address chris@thenakedscientist.com.
Now it's time to return to our pop-tastic kitchen science and find out how corn kernels can pop new technologies into the minds of engineers and inventors. Earlier on, Ben and Dave took a heavy object to some innocent popcorn kernels, and while leaving the others untouched, looking on in despair. Let's find out what happened next.
Welcome back to Kitchen Science. Today we're playing with the properties of popcorn. So Dave, what did we want people at home to try out?
We'll try popping some normal popping corn, and just to check it's working, and then try popping some popcorn which you just crack the kernels off and see whether that works as well.
Well, we've got a good handful of these cracked kernels now, so I think we should probably get the hob on. Now, we've already heated this oil up a bit just to speed things along, but I'll just put the hob on again and get it reheated. Okay, well, while that gets hot enough to actually pop our corn, what actually is popcorn?
Popping corn is basically the seed of a type of maize plant. Sweet corn is another type of maize plant. And there's lots of others which are used, often ground up to form cornmeal or corn flour.
So could you actually do this with sweet corn? Could you pop sweet corn?
Popping corn has been especially bred to be particularly good at popping, and you really want a kind of maize which has dried out, so there's not too much water in the kernels. So possibly not sweet corn. Other kinds of maize would kind of work okay, but popping corn is the best.
Okay, well, I think this oil should be hot enough now, so let's throw in a handful of your cracked kernels. Now, these are the ones where you've broken the actual surface, so let's just throw a few in to the nice hot oil, see what happens. Well, even before I'd got the lid on properly, I could see that some of them had kind of started to grow and expand a bit. They're just sort of becoming really tiny baby popcorn, and without going pop.
What's happening is that inside the grain, there's a whole lot of starch. This starch is fuel for the seedling, so it can get quite big before it needs to get to any light and photosynthesize. And that starch's got a little bit of water in it. When you heat it up, it turns a bit like into something like a jelly, a bit like when you heat up corn flour in water.
These are burning now, so I'm going to take them off the heat. But popcorn doesn't normally burn quite that quickly. So starch turns into a sort of goo, and that's why we put it in soup and that sort of thing to thicken it up. What's that got to do with the popcorn?
Well, then when you get it very, very hot, the water inside it boils. When water boils, it expands by 1,000 or 2,000 times. That blows up the starch and makes a foam. And that foam is the popcorn, which you can see. And that foam has been growing slowly as the water boils out of the cracked corns.
So these cracked corns have been kind of extruding small bits of this foam starch that is really what popcorn is. Why doesn't that happen when you put the normal, non-damaged kernels in? How come they go pop?
Well, should we try it?
Okay, then I'll get this oil hot again, and let's throw in a few undamaged kernels. Okay, now they're sizzling away nicely, but they're definitely not extruding like the other ones did. They're not growing yet.
Well, the reason is that the outer layer of a popping corn is actually very, very, very strong. It's both waterproof and gas tight, and it'll take a pressure of up to about 10 atmospheres.
So this huge pressure inside them must be why it goes pop.
Yes, eventually they fail explosively with a great big pop.
Well, these have all popped now, so I'll just turn it off again. And if we let them cool down, we can taste one. Do be careful when you're doing this at home, of course, because freshly popped popcorn is really very hot. But these are a great deal bigger than the cracked ones that you've done. But surely there's the same amount of starch there. It all expands by the same amount when you heat it. So wouldn't it just be the same amount of actual popcorn, but these ones formed in an explosion instead of an extrusion?
Well, there's two effects. One of them is that if there's a hole on the side of your popcorn, then the gas can escape slowly. So not all of it is used to blow up the foam and make a big foam. And the other one is that if you keep water under pressure as it gets hot, it'll actually boil at a higher temperature. This is how a pressure cooker works. So the temperature inside the kernels can get up to maybe 180 degrees centigrade, but when it goes pop. This means that when it actually goes pop, it'll expand a lot more and blow up the foam bigger.
So that's how proper popcorn actually works. Now let's just taste these. That's delicious. I think perhaps a little bit of salt.
I would certainly help, yeah.
So that's how popcorn works, and that's why it makes this wonderful stuff. But is this something that we've copied? Today's show is all about how we've been inspired by nature to make interesting materials. Have we copied the popcorn trick?
I don't know if it was copied directly, but certainly various parts of the trick are used in technology. For example, if you want to make a nice foamy plastic, what you do is you get something like polystyrene plastic, which is the same plastic that you use to make model aeroplanes out of. You dissolve lots of gas in it at high pressure, then you suddenly let the pressure off, it expands very quickly, and it blows a nice foam, which makes polystyrene packaging.
So polystyrene and popcorn actually have a lot in common, although popcorn tastes an awful lot better.
That's right. And the pop is actually also used in technology because things like gunpowder, if you set it off, it doesn't actually go bang. It will just burn very quickly with a whoosh. But if you seal it inside a paper cylinder and then you set it off, it produces lots and lots of gas, which the pressure builds up and up and up until the paper cylinder fails and it goes pop or bang.
And that's how you make fireworks. So the science of popcorn is also the science of polystyrene packaging and the science of fireworks. Now that's brilliant, but let's make a little bit more popcorn so we can get on with watching our film. We'll be back with more kitchen science next week.
So the combination of the airtight container and lots of pressure creates those lovely mini explosions in popcorn. You can watch those explosions in super slow motion thanks to Dave's wonderful camera on our website. And you can find this volatile footage at thenakedscientist.com/kitchen science. Now, just before we run out of time, we've got a question for you, Chris, from Andrea Tembrell, talking about borrowing from nature. They want to know, do viruses have a metabolism?
Yeah, because, of course, this is interesting in the context of biomimetics because people are talking about using viruses and their ability to infect cells and put their DNA and RNA into cells for gene therapy. So it's an important question. And the answer is no, viruses are not alive. They don't have a metabolism. They're nothing more than an infectious bag of genes, which is able to put that gene into a cell and make the cell then start to produce all of the viral products to make more viruses. That's all they do. Now, one quick one for you, Kat. Kevin Daly says, does your DNA change throughout your lifetime?
I could talk about this one for hours, but basically, yes, it does. You pick up mistakes as you go through your life in your DNA due to damage from things like tobacco smoke, from the sun, just from your own metabolism, and that's eventually what causes things like cancer. And also you get what's called epigenetic changes. There's changes to the kind of the code around your DNA. So yeah, your DNA is very different when you're older from when you're younger.
I think mine certainly is. Thank you, Kat. Right, well, that's all we've got time for this week. I have to say thank you to Julie Seagrave, Chris Elvin, Andy McIntosh, Jim Platts and David Henke, who all contributed this week, and to our wonderful production team, Dave Ansell, Ben Vausler, Miracintha Lingham, Tom Simpkins and Diana O'Carroll. Next week, the buildings of the future. How can you design buildings that don't need aircon? We'll find out.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.